Some differential equations are difficult to solve analytically or even impossible to solve. And then some graphical approach is very useful. We have seen in the previous part the differential equation y derivative is minus 2xy. And we have found the solution that was e to minus x squared times a constant. Because when we differentiate this, we get the function itself times minus 2x, which is the derivative of the given function. And e to minus x squared is a well-known function, use Gaussian. And for k is 0, this is the constant 0 function. For k is positive, it looks like that. And for k is negative, it looks like that. Okay, so this was possible when we solved the equation. But we can sketch this graph even without having the analytic solution. Consider just various value of x and y, that means various points in the xy plane, and we can evaluate the derivative. When the derivative is positive, then we draw a little arrow going up. When the derivative is negative, then we draw an arrow going down. And in this way, we can fill the plane with little arrows, and they will show us the direction in which these graphs go. Let me illustrate this in this example. Say in the first quadrant, when x is positive, y is positive, 2 is positive, so this product is positive, and we have minus. So the derivative will be negative, and negative derivative means decreasing function. If we go to the left, then x changes the sign, and this expression changes the sign from negative to positive. On the way from the right to the left, x crosses 0, and when x is 0, the derivative is 0, and if it is 0 or close to 0, then the function is close to a constant function. And for negative y, everything changes. It was positive here, it was negative here, so it will be positive. Here it was positive, so it will be negative. And once again, if x is 0 and y is negative, the derivative is 0. And if we sketch a lot of arrows like that, then you see, if you follow the arrows, then you get a similar picture like that. Without solving the equation, you see. And from this picture, we can also find some important properties of the solution. Say, what about the extrema? At these points, on the positive y semi-axis, x is 0, and the derivative is 0. And when you follow the lines, then changing x from negative to positive, for positive y, changes the derivative from positive to negative. That means the function changes from increasing to decreasing, and it will have a maximum at the points on the positive semi-axis, y semi-axis. And similarly here, the derivative crosses 0 when x crosses 0, and the derivative changes from negative to positive. That means the function changes from decreasing to increasing, and it will have a minimum. So we can say a lot about the solution even without solving the equation, just by considering this system of arrows, this directional field of the differential equation. So this is a good way to solve equation where the right-hand side depends on x and y. And in a still simplified case, when the right-hand side depends on y only, no x, that means the differential equation is autonomous, then another approach is useful. Consider the differential equation, say y derivative is 1 minus y squared. Or let's start with this very simple equation, y derivative is equal to y. Or better to say 2y, to have something less trivial. If we plot this as a dependence of y derivative on y, then we have this function. Y derivative is 2y. Don't be confused with the axis. In most cases, we use the horizontal axis to plot x, the independent variable, and we use the vertical axis to plot y, the dependent variable. Now, we use the x-axis to plot y, which is for the function the dependent variable. And here we plot y derivative, which is something completely new, which we did not plot here. But if we consider the general equation of that, f is some expression depending on y only, no x for the moment, then we can plot the graph of f. And again, well, this equation is very easy, we can solve the equation. But assume we don't want, we don't like, we don't know how to solve, and we just want to practice the graphical approach. For positive y, the derivative is positive, and positive derivative means increasing function, so y will grow. For y is 0, the derivative is 0, and y will stay 0 forever. And for negative y, the derivative is negative, and negative derivative means decreasing y, so we will move to the left. And this is in good agreement if we plot the solution, which is some exponential. It looks like that. Positive y will grow to more positive, to higher values. Negative y will go down to more negative, and 0y will stay 0. If we have the differential equation y derivative is minus 2y, then the dependence of the derivative as the function of y looks like that. Minus 2y is a line like that. And once again, for positive y, we have negative derivative, but negative derivative means decreasing. So positive initial value of y will decrease, will go to the left. On the other hand, negative y results in positive derivative, and positive derivative means increasing values of y. And 0y remains 0 forever. So in these two cases, 0 is a sort of equilibrium or stationary point where nothing changes in x, where nothing changes in time. It stays constant forever. But this behavior is called unstable because some small deviation grows in time, like if you have a little ball on a hill. And this behavior is called stable because differences decrease in time. So stable behavior looks like a ball in a cup, because if you displace the ball to the side, it returns back. In a more general case, like y derivative is sine of y. If you sketch the graph of sine, once again, this is not x, this is y, and this is not y, this is y derivative. Then, when y is 0, the derivative is 0, and it stays forever. Here we plot x and y. So 0 is a solution. There is another constant solution, namely x is pi. Y is pi. When y is pi, the derivative is 0, and we have again a constant solution. And now, for values of y between 0 and pi, say this one, the derivative is positive, and positive derivative means increasing behavior. So y will grow, and as y approaches pi from the left, the derivative will be very small, so it will grow like that. And then it will be almost constant. That is the future. And the history, y comes from values close to 0. Then we have another stationary solution, namely 2 pi. And y values between pi and 2 pi, something like that, result in negative derivative. And the negative derivative means y values will decrease, and these values were increasing. So in the interval between pi and 2 pi, the solution will look like that. And this is not the only solution. There will be many of them looking like that. And similar here. Well, in the same case here, for y is 3 pi, the derivative is 0, and we have another constant solution. And for y values between 2 pi and 3 pi, the derivative is positive, so y is increasing. So you see, we can say a lot about the solution even without solving, just using these pictures. This is a very useful method. Before we clear this, so we see that the integer multiples of pi are stationary points, are equilibrium points corresponding to stationary solutions. And if the graph goes this way, from positive to negative, then this stationary point is stable. And if this graph is increasing, then small deviation to the right results in positive derivative, that means increasing, and small deviation to the left results in negative derivative, that means decreasing. So this is unstable and this is stable.